7 Brief Lessons on Physics by Carlo Rovelli. Picture this, a young man, barely older than a college student today, spending an entire year doing absolutely nothing productive. He's ditched his strict German school, fled to sunny Pavia, Italy, and joined his family there. Sure, he drops into a university lecture here and there when the mood strikes him, but mostly, he's just reading philosophy, taking long walks, and gloriously wasting time. Meanwhile, his father's out there installing cutting-edge electrical power plants, bringing the roar of industry to Italy. But his son, Albert Einstein, is basically the original couch surfer. Here's the kicker, though. It's during this supposedly wasted year that something extraordinary is quietly brewing. Our author today reminds us of something parents of teenagers desperately need to hear. You don't get anywhere by not wasting time. That aimless young wanderer would eventually tear down everything we thought we knew about reality and build it back up again from scratch. And that's exactly what our book today is about. 7 Brief Lessons on Physics is your personal invitation into that rebuilt reality. The author, Carlo Rovelli, isn't just a brilliant theoretical physicist leading a quantum gravity research team in France. He's also someone who can actually make you fall in love with physics. He wrote these lessons specifically for people who think physics is way over their heads. And guess what? It became an instant #1 bestseller in Italy and has been devoured by millions of readers across dozens of languages. People who never imagined they could understand physics, let alone enjoy it, couldn't put it down. Why did it capture so many hearts? Because Rovelli doesn't just dump facts on you. He gives you wonder. He pulls back the curtain on everyday life to reveal the absolutely wild, gorgeous, and deeply weird universe hiding just underneath. So here's my promise. Stick with me through this journey, and you won't just walk away with some cool party facts. You'll see everything differently. The stars overhead, the way time passes, even the room you're sitting in right now. None of it will seem like a boring, fixed backdrop anymore. You'll see it all as a dynamic, shimmering, unfinished story. And best of all, you'll finally understand your own place in that story in a way that'll blow your mind. Ready? Let's dive in. Our story picks up after Einstein's loafing year wraps up. He dives deep into physics, and in 1905, he fires off 3 papers to a major scientific journal. Each one is an absolute knockout. The first proves atoms are actually real. The second kicks off the bizarre new field of quantum mechanics. And the third introduces his first theory of relativity, the one showing that time is seriously weird. You know that classic thought experiment? A twin zooms off at crazy speeds and comes back younger than their stay-at-home sibling? That's this theory in action. Einstein becomes an overnight sensation. But something's gnawing at him. His shiny new relativity theory doesn't play nice with gravity. For over 200 years, everyone had bought Isaac Newton's version of how things work. Newton pictured space as this giant, empty box. A fixed stage where objects cruise in straight lines unless something pushes them. Gravity was this mysterious, invisible force, somehow reaching across empty space to yank things together. Even Newton himself was pretty uncomfortable with how that could possibly work without anything connecting objects. Einstein obsessed over this problem for a solid decade. 10 years of hitting dead ends, having brilliant breakthroughs, and then spiraling back into total confusion. Finally, in 1915, he cracks it. His solution becomes the general theory of relativity. The legendary physicist Lev Landau later called it the most beautiful of theories. And the central insight? absolutely breathtaking in its simplicity. Einstein had this stroke of pure genius. He realized the gravitational field isn't something floating around in space. The gravitational field is space itself. Let me paint you a picture. Imagine stretching out a big rubber sheet. Now drop a heavy bowling ball in the middle. What happens? The sheet curves and dips down around it. Roll a marble nearby, and it won't travel straight. It'll follow that curve created by the bowling ball, spiraling around it. That's literally what's happening in our solar system. The sun is that bowling ball. It's so ridiculously massive that it actually bends the fabric of space-time around itself. And Earth, like that marble, isn't being mysteriously pulled by some invisible force. It's just following the curve. It's traveling in a straight line through bent space. We're not living inside some rigid, invisible box. We're swimming through this gigantic, flexible, cosmic structure that can ripple, flex, and twist. Planets circle the sun, and apples fall from trees simply because space itself is curved. This one beautiful idea unleashed predictions that sounded absolutely insane, but one by one they've all come true. The theory predicted that not just space but time itself can bend. Time actually passes slower when you're closer to something massive. We've measured this. Someone living at sea level ages just slightly slower than their identical twin living in the mountains. GPS satellites have to account for this effect, or your directions would be miles off every single day. It predicted that when a truly gigantic star dies, it can collapse so hard under its own weight that it bends space so severely it literally punches a hole through it. Nothing can escape from this hole, not even light. These are the famous black holes. When Rovelli was a student, they were just wild speculation. Today, astronomers have spotted hundreds of them. And perhaps most mind-blowing of all, Einstein's equations showed that the entire fabric of space can't just sit still. It has to be expanding. This meant the universe must have started from a single, incredibly tiny, unimaginably hot and dense point that exploded outward. We call it the Big Bang. And back in the 1960s, scientists actually discovered the leftover warmth from that initial explosion, a cosmic background radiation filling all of space, confirming the prediction was spot on. This is the world of general relativity, a universe where entire cosmos explode into being, where space collapses into bottomless pits, and where the fabric of reality ripples and sways like ocean waves. It's a masterpiece, a stunning and coherent vision of the universe at its most grand and epic scale. But here's the thing, it's only half the story. Right when Einstein was perfecting his cosmic vision, another gang of brilliant young physicists, led by Denmark's Niels Bohr, was exploring the complete opposite end of things. They weren't looking at vast cosmic expanses. They were peering into the tiniest bits of matter, atoms and the particles inside them. And what they discovered would absolutely shatter everything we thought we knew about reality. This new science is called quantum mechanics. And where relativity is this tight, elegant gem created by essentially one brilliant mind, quantum theory is this sprawling, mysterious, profoundly bizarre construction that still makes our heads spin a century later. It all kicked off in 1900 when German physicist Max Planck was wrestling with a problem about heat. He came up with this clever mathematical trick. Instead of imagining energy as smooth and continuous, like water pouring from a faucet, he pictured it coming in tiny separate packets or chunks, which he called quanta. His math worked perfectly, but physically, it made zero sense. 5 years later, Einstein again stepped up and realized these quanta weren't just a mathematical trick. They were real. He showed that light itself is made of these little packets, these particles of light we now call photons. This was quantum theory's true birth. But then things got really weird, going in directions that even Einstein, its own parent, absolutely hated. A young German genius named Werner Heisenberg grabbed the core idea and pushed it to its terrifying conclusion. He proposed that electrons don't really exist the way we normally think things exist. An electron doesn't have a specific position until it bumps into something else. When nobody's looking or measuring it, it's not anywhere in particular. It exists as this cloud of probability. It only pops into a specific location, completely at random, when it collides with something. Just sit with that for a second. The fundamental building blocks of everything aren't solid little marbles. They're ghostly, fuzzy things that only become real through interaction. Reality, at its deepest level, isn't a collection of things. It's a web of relationships. Rovelli puts it beautifully. It's as if God sketched reality not with bold, solid lines, but just dotted it with a faint outline. And there's more weirdness. These quantum jumps aren't predictable. We can never know for certain where an electron will pop up. All we can calculate is the probability it'll show up here or there. This injection of pure randomness into the heart of physics drove Einstein absolutely crazy. He famously complained, "God does not play dice." For years, Einstein and Bohr engaged in this profound philosophical boxing match. Einstein would dream up clever thought experiments to expose how absurd the new theory was. Imagine a box filled with light. He'd begin. And every single time, Bohr would patiently work through it and show how the quantum world, weird as it was, stayed internally consistent. Eventually, Einstein had to admit the theory worked, but he remained convinced something deeper and more sensible had to be hiding underneath. Years after Bohr died, someone photographed the blackboard in his study. On it was a drawing of the light-filled box from Einstein's thought experiment. Even at the very end, he was still wrestling with the mystery. And that mystery hasn't gone away. So now we're standing between these two towering pillars of 20th century physics. One is general relativity, Einstein's flawless theory of the really big stuff. Planets, stars, galaxies, the expanding universe. The other is quantum mechanics, the wildly successful but deeply strange theory of the really tiny stuff, atoms, particles, and the probabilistic weirdness underlying all chemistry and modern technology. Both theories work incredibly well. And yet they can't both be right, at least not as currently written, because they flat out contradict each other. This is the massive puzzle at the heart of modern physics. In general relativity's world, space is smooth and continuous, curving gracefully. In quantum mechanics' world, everything is grainy, jumpy, and probabilistic, happening on a fixed, flat stage. The two theories might as well be speaking completely different languages. Students taking classes in both might wonder if their professors have ever actually talked to each other. And this is where the real cutting-edge adventure in physics is happening right now. Out on the frontier, beyond what we solidly know, scientists like Carlo Rovelli are trying to crack this puzzle. They're hunting for a single unified theory of quantum gravity that can marry these two conflicting pillars and give us one coherent picture of how everything works. One of the most promising approaches is called loop quantum gravity, a field where Rovelli himself is a pioneer. The core idea is, once again, stunningly simple. It tries to take both great theories seriously. General relativity taught us that space is dynamic, something that can stretch and twist. Quantum mechanics taught us that fields like this are made of quanta-discrete grains. So what happens if you apply quantum thinking to space itself? The immediate answer: space isn't continuous. It's not infinitely divisible. It must be built from tiny, indivisible grains or atoms of space. These grains are insanely small, a billion times smaller than the smallest atomic nucleus. In this theory, these space atoms are called loops, and they're linked together in a network, weaving the texture of space like rings in cosmic chainmail. So where are these quanta of space? Nowhere. They aren't in space. They are space. Space is created by the relationships between them. The illusion of smooth, continuous space around us just comes from our blurry, big-picture view. It's like looking at a calm mountain lake from a distance. It seems perfectly smooth and still, but we know it's actually made of countless frantic, bouncing water molecules. Same deal with the fabric of space-time. But the most radical consequence of this theory? It completely upends time. Just as smooth, continuous space disappears, so does the idea of universal, flowing time. The fundamental equations don't even have a variable for time. This doesn't mean everything freezes. It means change is everywhere, but it doesn't happen to one universal beat. At the fundamental level, there's no master clock. Each process dances to its own rhythm. Time isn't a river carrying everything along. Time emerges from the relationships between quantum events themselves. This radical idea might even reshape how we understand the Big Bang. If space has a minimum possible size, then the universe couldn't have been squeezed into an infinitely tiny point. The loop theory equations suggest our Big Bang might actually have been a big bounce. Our universe might have been born from a previous universe that contracted, squeezed down to the smallest possible size, and then bounced back out, starting the expansion we see today. At that bounce moment, time and space as we know them would have dissolved into a probabilistic fog. This brings us to one final profound mystery. Why does time seem to flow in only one direction? Why do we remember the past but not the future? The answer, surprisingly, involves heat. Think about it. A frictionless pendulum could swing forever, and if you filmed it and played it backward, it would look totally normal. But add friction, and the pendulum heats up its supports, loses energy, and slows down. That process creates heat, and suddenly you can instantly tell past from future. You'll never see a stopped pendulum spontaneously start swinging by, sucking heat from its surroundings. The difference between past and future only shows up when heat's involved. Austrian physicist Ludwig Boltzmann figured out why. Heat always flows from hot to cold, not because of some absolute law, but because of probability. It's just statistically way more likely for a fast-moving molecule in a hot object to transfer energy to a slow-moving one in a cold object than the reverse. The flow of time, the very distinction between past and future, is rooted in chance. But it's also rooted in our limited perspective. The arrow of time appears because we don't track every single molecule. We only interact with the world through a limited slice of its properties: temperature, pressure, shape. Our sense of time flowing emerges from this incomplete knowledge. For a hypothetical being who could see every quantum interaction in the universe, past, present, and future would all exist simultaneously, a single unified block. As Einstein once wrote to his lifelong friend's sister after the friend died, people like us, who believe in physics, know that the distinction between past, present, and future is nothing more than a persistent, stubborn illusion. And this is where all three great mysteries converge. general relativity, quantum mechanics, and the nature of time and heat. And the key, the Rosetta Stone that might finally crack them all open, may come from the strangest objects in the universe, black holes. The great Stephen Hawking showed that if you apply quantum mechanics to a black hole's gravitational field, you discover something incredible. Black holes are hot. They emit faint heat, a thermal radiation. This is a quantum effect happening to a gravitational object, producing a thermal result. It's the first phenomenon we've ever found involving all three pieces of the puzzle. There, at the edge of black holes, we may finally begin to grasp the true nature of time. So after this whirlwind tour through exploding universes, quantum weirdness, and vanishing time, we need to return to the question that matters most. What about us? In this vast, glowing cosmos, this swarm of ephemeral quanta and rippling space-time, what are we? If all of reality is just a giant jigsaw puzzle of particles and fields, where do our feelings, our dreams, our sense of self come from? Carlo Rovelli ends his lessons by turning from the cosmos to ourselves, and what he offers isn't cold or sterile, it's deeply moving and profoundly human. We're not outside observers of this universe. We're woven right into it. We're made of the exact same atoms, the same stardust, as the galaxies themselves. For centuries we've been on this humbling journey of discovery. We thought we were at the universe's center, and learned we're on a small planet in a remote corner of countless galaxies. We thought we were completely separate from all other species, and learned we share ancestors with butterflies and oak trees. Like children growing up, we're slowly learning the world doesn't revolve around us. And in this process, in being reflected by reality's vastness, we're finally learning who we truly are. The world Rovelli describes doesn't diminish our humanity. It's the very source of it. Our emotions, our values, our capacity for love, these aren't less real for being part of nature. They're more real. They're the complex, beautiful form that nature has taken right here, in us. Even our sense of free will finds its home here. Being free doesn't mean magically breaking physics laws. It means our actions are determined by nature's laws acting inside us. In the impossibly complex and fleeting interactions between the 100 billion neurons in our brains, when you make a decision, it truly is you deciding, because you aren't some ghost haunting a machine. You are the machine. You are the whole intricate, wondrous process. So what can we take from these lessons today? Let me suggest two simple things. First, next time you get the chance, go outside on a clear night and really look at the sky. Don't just see dots of light. Try to feel the reality behind them. See the starlight that's traveled millions of years to reach your eyes, its path bent by space's curvature. Feel yourself on a spinning planet, flying through a universe born in fire and still expanding. Connect with that sense of awe. Second, embrace your curiosity. It's in our nature to want to know more, to learn, to explore. That drive is the same force that led Einstein to his revelations and Rovelli to his. It's the engine of science. Don't let anyone tell you these big questions aren't for you. They're for everyone. This small book testifies to curiosity's power. It reminds us that science isn't some dry collection of facts. It's a story, a grand adventure. It's the story of us trying to follow reality's tracks, to understand our home a little better. And the most beautiful part? The story isn't finished. We're living right at the edge of what we know, touching the vast ocean of the unknown. And there, at that boundary, the mystery and beauty of the world truly shine. As Rovelli says in his final words, it's breathtaking. That was a summary of 7 Brief Lessons on Physics by Carlo Rovelli. We've definitely covered the major ideas today, but I'll be honest, a summary can only ever be a map. The real magic happens when you walk the territory yourself. It's in those quiet moments when Rovelli's elegant prose or a particular mind-bending idea connects with you in ways you didn't expect. This summary is designed to help you decide if this book deserves your time. If anything we've discussed today has sparked wonder in you, grab a copy. Reading it isn't just about learning. It's an experience that can genuinely change how you see the world and your place in it. A link to the book is in the description. Also, if you found this journey valuable, please click that like button and subscribe to the channel. It lets me know these deep dives are helpful and ensures you won't miss our next exploration into another life-changing book. Let's keep learning together.